This episode is brought to you by Brilliant. This peculiar yet familiar looking structure is called a brake node. It's a component that integrates both a braking system and a suspension upright into a single, efficient unit that weighs just under 3 kilograms. It's one of over 350 revolutionary components that can be found on the Czinger 21C Hypercar concept. The unique organic appearance of these parts is a direct result of a revolutionary approach to vehicle manufacturing being pioneered by its creator, Divergent 3D. The results of these developments are a clean, true 1-to-1 power-to-weight ratio with unprecedented acceleration figures for its class, particularly in its claim of a 0 to 248 to 0 mph time of just 29 seconds. However, beyond these incredible performance figures, the Czinger 21C represents a milestone for Divergent 3D's goal to mass-produce vehicles with limited or no direct tooling in a fully digital, end-to-end integrated system called the Divergent Adaptive Production System, or DAPS. DAPS relies upon Metal Additive Manufacturing to produce complex, highly efficient integrated structures. But the true power behind Divergent 3D's process is their approach to component design that employs AI to rapidly create complex yet highly optimized structures using generative design. Generative design is not a specific technique, but rather a software-based design exploration process. Conceptually, a designer defines the design goals into generative design software, along with parameters such as structural performance, spatial requirements, manufacturing methods, and cost constraints. From these inputs, the software rapidly examines a large set of possible solutions, testing, learning, and refining from each interaction to produce an optimized result. It's important to note that generative design is not intended to replace human designers, but rather augment their capabilities by providing them with new insight by uncovering innovative and unconventional design solutions that might not be immediately apparent. By exploring a vast design space, generative design can discover novel shapes, structures, and configurations that maximize performance and efficiency, particularly in complex and multidisciplinary design domains. However, designers still play a critical role in defining design goals, interpreting the generated results, and incorporating their creativity and domain expertise into the final design. To understand how generative design is used in practice, let's look at the simple hub. This simple component must have 4 fixed mounting points that support a specific force through a central through-hole. Both the position and size of the mounting points and the center are predefined and are immutable. Aside from the force requirements, the part must also be light as possible and designed to be manufactured using the subtractive process of milling, with aluminum being the chosen material. Initially, a designer would approach this in a traditional manner, creating a simple plate of a constant thickness with a slightly thickened rim around the center to accommodate the mating component that transmits the expected force. The overall thickness of the part is based on the amount of distortion displacement allowed for the specified operational force. In this example, the initial design can handle up to 10 times the expected force before exceeding the design limitation. While this initial design is acceptable, it contains a large amount of unneeded material. With a generative design approach, an analysis of how the component reacts to the anticipated force is first done. From this information, the generative design algorithm iterates through a series of changes to the topology of the component based on a specific design goal until an optimized solution is reached. For the hub, the goal is weight, so material that does not contribute significantly to the component's performance is whittled away, leaving a highly optimized organic shape that reacts similarly to the original heavier design. It's important to note that while the algorithm-designed part may be ideal for the constraints presented to it, it may contain flaws such as compromised strength in unspecified modes and topology irregularities that would make assembly impossible. It can also produce parts that are impossible to manufacture or easily fixture. Ultimately, the designer must determine what constraints are provided to the algorithm and how to utilize the solution produced. Part features may be excluded from optimization, and even the final solution itself may just be used as a guide for a more traditional design that incorporates cues from the algorithm's solution. Though overall, an optimized part design is produced far more rapidly than the traditional process of creating and modifying designs based on a designer's expertise and intuition. While there is no de facto method to implementing generative design for part development, the technology typically adopts one of 5 adaptive computational approaches. Cellular automata are mathematical models used to simulate complex systems consisting of discrete cells or units that interact with their neighbors according to a set of predefined rules. Each cell can be in a particular state, and its state evolves over time based on the state of its neighboring cells. A cellular automaton is typically represented as a grid of cells where each cell possesses a finite number of states. The grid is defined in any number of dimensions, with 3 dimensions being used for part design. The state of each cell is updated in discrete time steps according to a set of transition rules. The behavior of a cellular automaton emerges from the interactions and the local rules and design constraints that govern these state transitions. From this, complex patterns and phenomena can arise, often exhibiting properties such as self-organization, pattern formation, and the emergence of a global behavior. However, the solutions produced can be complex and difficult to predict, while also requiring a large amount of computing power as the model's cell density increases, though it works well with parallel computing. They're also limited in use to bottom-up designs with very little adjustability beyond initial rules and constraints, effectively only producing emergent, context-sensitive solutions. One example of cellular automata is the generation of lightweight lattice patterns for structural panels. In this use case, the rules that govern cell growth and connectivity are used to iteratively generate lattice patterns that maximize load-bearing capabilities while minimizing material usage. In general, cellular automata generative design tends to work well with design challenges with repeating elements, such as in the case of architecture. Genetic algorithms are a class of optimization techniques inspired by the process of natural selection and evolution by representing potential solutions to a problem as individuals in a population. These individuals are represented by characteristics data that form their genotypes. This genotype is used to evaluate the individual's fitness based on how well it solves the target problem. The key to how a genetic algorithm operates is in its cyclic nature of generation creation. Initially, a population is randomly generated to start the optimization process. The fitness of each individual in the population is assessed by evaluating how well it performs in solving the problem. Next, individuals are randomly selected for reproduction, with higher fitness individuals having a greater chance for the process. In reproduction, the selected individuals are used to create offspring, where the genotype from 2 parents are used to create new individuals, while mutations are introduced as small random changes. The new offspring now replace some individuals in the previous generation, ensuring that the population size remains constant while promoting the propagation of a potentially better solution over generations. The algorithm continues iterating through generations until a termination criterion is met. This criterion can be a maximum number of generations, reaching a desired fitness level, or when improvement stalls. Through successive generations, the algorithm evolves the population towards more optimal solutions. To understand how a genetic algorithm can be used to optimize a part for minimal weight while maintaining structural strength and satisfying manufacturing constraints, let's look at a connecting rod. A connecting rod design can be represented as a genotype of parameters encoding characteristics such as length, width, thickness, material choices, and geometric features. From this, a population of diverse connecting rod designs is randomly generated, with each individual having a unique set of parameter values. Each connecting rod design is then evaluated based on a fitness function that combines weight reduction, structural integrity, and manufacturability. The fitness function considers factors like stress analysis, finite element analysis, fatigue life estimation, and manufacturing cost estimation, quantifying the quality of each design. Individuals with higher fitness values, indicating lightweight yet structurally robust designs, are more likely to be selected as parents for the next generation. Random changes within predefined bounds are introduced as mutations to the parameter values of offspring designs to promote exploration. The offspring designs replace a portion of the existing population based on their fitness values. This allows promising designs to persist while introducing diversity. As the genetic algorithm progresses through generations, it explores and refines the design. From this, promising design variations emerge from the iterative process, ultimately yielding an optimized connecting rod design. While genetic algorithms are extremely versatile, work well with parallel computing, and are well suited to top-down designs, their effectiveness is limited by the way the key design characteristics are mapped to a genotype, as well as the robustness of the fitness function used to guide generational evolution. Shape grammar is another powerful technique used in generative design to explore complex and varied designs. Similar to cellular automata, it enables the generation of designs by specifying rules that define the relationships between the system's fundamental elements. However, instead of cells, shape grammar employs a vocabulary of basic shape elements, such as lines, curves, polygons, or 3D primitives. These shape elements serve as the building blocks for the generative design process. From this, a set of rules are then applied that define how these elements can be combined and transformed. Each rule consists of a condition and an action. The condition specifies the context in which the rule can be applied, such as the presence of a specific shape or spatial relationships. The action defines the transformation or replacement that occurs when the rule is applied, such as adding, modifying, or deleting shapes. Within the context of generative design, an iterative process of applying the rules to an initial collection of shapes is repeated multiple times, allowing for the gradual expansion and refinement of a design. Shape grammar allows for the incorporation of randomness in the generative design process to encourage variations in the generated designs. Constraints are also imposed on the generated designs, such as structural integrity, manufacturability, or specific spatial relationships. Much like genetic algorithms, the generated designs are evaluated based on predefined metrics similar to a fitness function that capture the desired design objectives. These highest performing designs can now have their parameters further adjusted and the iteration process repeated in search of a higher fitness level, further optimizing the design. Shape grammar in generative design is especially suited for aesthetic design exploration, such as a taillight assembly, for example. To generate a range of unique taillight designs that exhibit different shapes and configurations while considering functional requirements, a vocabulary of basic shapes such as rectangles, circles, and curves are used. From these, rules that create contours from rectangles, create accents from curved edges, and repeat circular elements are used to interactively produce a variety of potential designs. Constraints such as size limitations, legal restrictions, light distribution, and visibility are also applied to these designs. From the produced results, the designs that best meet the criterion are chosen, and further tweaking of the generative parameters are further explored, with the final product being used as the basis for a fully realized design. Beyond aesthetic exploration in parts, much like cellular automata, shape design works well in repeated structure designs, and is especially well suited to generative design use in architecture, such as for building design and site layout. Similarly, it's also bottom-up in nature, and issues with controlling localized behavior do emerge in larger designs as they grow, limiting the technique's use. L-system or Lindenmayer systems is a computational approach used in generative design to model the growth and development of complex structures such as plants, trees, or fractal patterns. Originally conceptualized by biologist Orested Lindenmayer in the 1960s to study the growth of plant cells, the technique was initially applied successfully to the field of computer graphics for modeling vegetation and landscapes, particularly in 3D environments. Much like shape grammar, L-system design is based on an initial condition with rules iteratively applied, though with symbols instead of shapes. The initial state, known as an axiom, begins with either a single symbol or a collection of symbols. The production rules in an L-system define how these symbols are transformed in each iteration. Each rule consists of a predecessor and successor. When a predecessor symbol is encountered, it is replaced by the corresponding successor symbols according to the defined rules. The symbols of the L system represent specific characteristics or action within a design. One of the more common interpretations are visual representations. For example, symbols can correspond to graphical elements such as lines or shapes, which are drawn to depict the evolving structure. However, the interpretation of the symbols can be extended beyond visual representations to other domains. While L systems are seen as more of an explorative tool in generative design, its flexibility in interpretation lends itself well to components deriving their performance from rule-based feature patterning, such as tire tread patterns, gear teeth patterns, and embedded antenna forms for wireless electronics. It can also be applied to aesthetic design applications, such as material textures, print patterns, and even wheel designs. Agent-based models are computational models that simulate the behavior and interactions of autonomous agents within a given system. Each individual agent follows its own rules and behaviors, collectively producing emergent patterns and system-level dynamics. By defining the interactions and rules within, designers can explore how these agents influence each other and their surroundings. These agents can represent various design elements, such as structural components, surface patterns, or functional parameters. The environment these agents operate in can also range from physical space to a network of relationships, and may even incorporate a fitness function that provides feedback of the design's effectiveness into the system. These interactions can be as simple as movement or communication, or more complex approaches involving decision-making and adaptation. The collective behavior of individual agents in the model leads to emergent patterns at the system level. These patterns can include cooperation, competition, social norms, or other complex phenomena that arise from the interaction and dynamics of the agents. These interactions can lead to the generation of unique and creative designs that would be challenging to conceive using traditional design methods. Let's look at how an agent-based model can be used to design a system. In this case, each agent represents a specific component of a suspension system. These agents are then assigned variables like spring stiffness, damping coefficient, link lengths, and pivot points. As the simulation begins, each agent follows predefined rules and behaviors. They adjust their values based on their interaction with other agents and the desired performance objectives. Throughout the simulation, the model evaluates the fitness of the suspension system designs through virtual vehicle testing, including simulation for ride quality, handling, stability, and tire contact, allowing the model to measure the performance of each design iteration. The agent-based model will iterate through multiple simulation cycles, constantly refining the design, collaborating and adjusting their values based on their interaction and the fitness evaluation results, ultimately leading to an optimized suspension system designed by finding an arrangement of agent values that maximize the desired performance criteria. Because agent-based models are so flexible, they can be applied either to top-down or bottom-up designs at any level of the design, from concept to realized geometry. However, this flexibility also makes their use more complicated, as the model's details, environment, testing, and the agent interaction rules must be robustly developed to produce useful results. Currently, generative design technology is still in its infancy, with various other types of computational models with vastly different goals being explored. These vary from neural network-based generative adversarial network models that can derive new ideas from existing designs, to variants on agent models that employ swarm intelligence. With the current aggressive rate of development, it's quite possible that in the coming years, AI will be able to design components at levels of complexity and effectiveness that are far beyond what's humanly possible in just seconds, and with that, redefining the roles of engineers and designers. The AI gold rush is very real, and with its recent expansion into mass accessibility, it has already demonstrated the potential to completely revamp how entire industries operate. In the world of design, AI is expected to bring about once unimaginable capabilities, particularly in idea exploration. Have you ever wanted to build an understanding of how the foundational concepts behind machine learning work? Well, there's a free and easy way to get started immediately. That's where Brilliant.org comes in. Brilliant.org is my go-to tool for diving headfirst into learning a new concept. It's a website and app built off the principle of active problem solving. Because to truly learn something, it takes more than just watching it. You have to experience it. Brilliant.org is constantly developing their courses to offer the most visual, hands-on approach possible to make mastering the key concepts behind today's technology effective and engaging. In fact, one of my go-to learning experiences is Brilliant's new Thinking in Code course. This intuitive progression of computer science lessons helps you develop a solid understanding of programming concepts by allowing you to build, examine, and self-discover the world of computation computation and algorithmic thinking using interactive exercises, setting the stage for a personal exploration into the world of machine learning. With Brilliant, you learn in depth and at your own pace. It's not about memorizing or regurgitating facts. You simply pick a course you're interested in and get started. If you feel stuck or made a mistake, an explanation is always available to help you through the learning process. To try everything Brilliant has to offer free for a full 30 days and start learning STEM today, visit brilliant.org/newmind or click on the link in the description. The first 200 of you will get 20% off Brilliant's annual premium subscription.